one thought led to another. It began while exploring the structure of pynastron and observing how a structural analysis program is organized. The graphical interface, the parser, the solver, and the results layer all seemed to have their own place. Then a different question appeared. At what scale are we actually looking at the world? That question became the starting point of this exploration. In structural engineering, we almost always work in millimeters, newtons, and megapascals. Plate thickness, deflection, crack width, and bolt diameter are commonly measured in millimeters. Human fabrication, machining, and construction all live in the millimeter world. Without noticing it, millimeters become the default lens through which we see structures. After years of structural design, a strange feeling begins to appear. Is 1 millimeter really that small? A 1 millimeter gap, a half millimeter step, or a barely noticeable vibration can feel surprisingly large to a person. And when we begin thinking about what happens inside a material, the question becomes even more interesting. Most change in nature and materials does not begin at the millimeter scale. It begins with microscopic cracks, grain boundary shifts, surface changes, contact evolution, corrosion, and moisture movement. Large failures that we can easily observe may simply be the accumulated result of changes that started much earlier in the micrometer world. Finite element method is a powerful approach. It views a structure as a sufficiently continuous material and builds its analysis around a stiffness matrix. HEM may begin from a different question. Where does change begin? Not at the scale of the whole structure, but at the scale of weakening relations, micro-openings, contact changes, and the first signs of separation. HEM does not need to calculate in micrometer units. The calculations may still use millimeters, newtons, and megapascals. What matters is the reference scale. Rather than starting from the size of a structure, HEM may start from the scale where change actually begins. One candidate for that starting point is the micrometer scale. The micrometer occupies a fascinating position. Atoms and molecules belong to the nanometer world. Human fabrication belongs to the millimeter world. Structures belong to the meter world. Between them lies the micrometer world, where materials, life, contact, cracks, surfaces, and human touch seem to meet. If HEM is built around seed, space, state, and relation, then the micrometer scale may become more than a unit of measurement. It may become the reference scale where change is born. Crack initiation may become micro-opening growth. Fracture may become accumulated weakening of relations. Space creation may become the beginning of separation. This is not a conclusion. It is not a declaration that the micrometer scale is the answer. Instead, it leaves an open question. At what scale should HEM choose to see the world? The search for that answer continues. Humanity has already built structures at the millimeter scale and explored the material world at the nanometer scale. But the world in between, the place where change may actually begin, could be less explored. HEM may be an attempt to enter that middle ground. Not to replace the worlds above or below, but to understand what happens in the space between them.